Okay, so in this question, we've got a disk that's spinning. They tell us it's spinning about an axis at its center, and there is friction between the axle and the disk, and that friction is exerting a constant torque. So that means there's a constant torque being exerted that's slowing this down. They tell us that at time t equals 0, the disk has an initial counterclockwise positive angular velocity. So counterclockwise, I assume they mean looking down on the disk. So that would mean it's rotating kind of in that direction. And the rotation axis would point up through its center, kind of like that. That would be the actual vector direction for that initial angular velocity. The disk later comes to rest at time t equals t1, and we're asked to sketch a couple graphs. So we know the angular velocity starts at omega naught. They tell us it's moving in the positive direction. It comes to rest at t1, and this is actually going to be a straight line. And the reason that it's a straight line, why we know that, is because, remember, we've got Newton's second law for rotations, t equals I alpha, and they tell us that the torque is constant. And if the torque is constant, the angular acceleration is constant. And if the angular acceleration is constant, the angular velocity should be changing at a constant rate. In other words, the slope of this line is constant. And to match it, we're going to have an angular acceleration graph that is also just of a constant value. Notice that it's negative, right, because the angular velocity is positive and it's slowing down. All right, for the next part of this question, they give us a few values. They give us the magnitude of the torque from friction, right? So that's just like the absolute value, right? That's the magnitude of it. And they ask us to find an equation for the rotational inertia in terms of these given variables and any physical constants. So that's stuff like G, right? Things that we know. Okay, so we're definitely going to have to use net torque equals I alpha, because this gives us our relationship between torque and I, right, which are two things that are given here. We don't know alpha, but we can find it because we have some other kinematics quantities. Now, looking at the kinematic stuff that they've given us, right, we know, let's think about what we know, right? We know the final angular velocity is 0. We know the initial angular velocity. We know the time interval. We don't know alpha. That's what we're looking for. And we don't know delta theta, which is not what we're looking for. So just looking over the kinematics equations, the one that has everything except for delta theta, angular displacement, is this one. So this is going to be the equation that we use. And this, if we solve this for alpha, it should let us get rid of that alpha here and get a relationship that we want. So we know that final angular velocity is 0. And if I solve for alpha, I get negative omega naught over, and this t is actually t1, negative omega naught over t1 equals alpha. And now I can put that in here. But we got to talk about this net torque a little bit. So one thing to keep in mind is, right, the angular velocity here, right, this was a positive number, right, that initial angular velocity. And notice that our angular acceleration is negative. It should be negative because it was slowing down, right? So we have a negative number here. That net torque should also be negative, right? They tell us the magnitude is T naught, but we know that it's acting in the negative direction. So we should really, when we fill out this equation, when we plug in the net torque, right, and friction is the only thing causing torque, we need to put a negative sign there. So that's our equation here. And if we solve it for I, we get I equals negative tau naught over alpha. And then we need to put these two equations together by plugging in that alpha there. And when I do that, that gives me I equals negative tau naught over negative omega naught over T1. And if I rearrange a little bit, the negative sign disappears. We've got tau naught T1 over omega naught. And that looks a little bit weird, but I think that what we could do is we could actually check the units just to make sure that what we're getting makes sense. So, actually, no, I don't want to do that. I don't think it's worth the time. Okay, so there we go. Now let's look at C. So for C, they're doing another experiment with the same disc, but now they start dripping oil in the contact surface between the axle and the disc to reduce the friction. And as time passes, the friction continues to decrease. And this starts happening at 1/2 T1. And they're asking us to sketch a new graph. So I think there's probably more than one correct answer they would accept here. But at first, we have the same behavior, right? That's slowing down from friction at a constant rate. But then after that, we start dripping in the oil, and there is less friction, right? So what that means is that there's still going to be friction, but not as much. And as we continue to drip the oil, the friction decreases. So the rate of the slowdown actually decreases. Maybe we should do the angular acceleration first, right? So we've got this constant acceleration due to torque. And then once we start dripping in the oil, the rate at which the acceleration decreases, right? If we write out our equation, it looks something like this, right? As we drip in the oil, this decreases over time, which means the angular acceleration decreases. So we could draw something like that. And I don't think we have enough information to really know what, like, is this going to be constant slope? Is it going to sort of like decrease over time, right? They don't tell us They don't tell us any information that would tell us whether this should be straight or not. So I think that this is suitable, and that means that this would have to be actually kind of something like that and be curved a little bit, like concave up, curved. And honestly, this one here, it could actually look kind of more like that, right? Where it is not just like constant slope, it could be kind of curved as well, but we just don't know. Okay, last part. The student is trying to mathematically model the magnitude tau of the torque, and the student gives these two equations, and we're supposed to basically figure out, well, which one of these makes more sense. So I think the best way to do this is just to really kind of look at the end behavior. So, for example, if we look at this first one, right, this is kind of a line equation, and what it looks like would be something like, it would start out negative, and then it would hit 0 at 1/2 T1. This one would, equation 1. Right, if we just think about it, right, if we plug in 1/2 T1 there, that's when we get 0. So this first equation is actually sort of, if we were to take our graph, let me redraw it to make it look nicer. Right, if we take our graph from above, oh, come on. No. And let me just check this really quick. I want to make sure I did this right. Okay, so here, for the first one, it's telling us that the torque, right? This is actually a graph of, they're modeling the torque over time. They're saying that the torque would be negative at first. No. At T1, the torque would be 0. 0 at 1/2 T1. So it would start there. And then it would actually kind of gradually become more and more positive. That's what equation 1 gives, which doesn't really make sense, right? Because the torque should have some, and again, I think this is also just the magnitude, so let's not worry about the sign too much. Right, so this is basically telling me that the torque starts at 0 at 1/2 T1, and then it actually increases, which doesn't really make sense, right? The torque should decrease as we go from 1/2 T1 to T1. So that one doesn't really work. Now, for number 2, this is a little bit more feasible, because for number 2, right, we can just kind of see that as T gets bigger, right, as T gets bigger, the torque, it decreases. And it continues to decrease kind of forever, right? So this equation here, this has behavior that's sort of more like a continuous decrease in torque as time gets bigger, which is what we would expect to see as we're dripping that oil on. So 2 is going to make a bit more sense. Sorry, I had to pause for a minute while I was working on this and just kind of think it through. But definitely equation 2, I think, is more feasible, right? Equation 1 has the torque actually increasing over time, right, as we go from 1/2 T1 onward. And number 2 has the torque decreasing over time as T gets bigger. All right, I hope this video was helpful.